So in this video, we're going to review a concept that we've already looked at in the course so far, the idea of a free body diagram. And we're also going to foreshadow a concept that we're going to talk about in more detail in the next module, which is describing the nature of the forces that support structures exert on a body when they're overcoming the loads that are applied to it. That is oftentimes referred to as the reaction forces of supports. And the reason that we're doing that second part is this lecture is organized a lot like the prior lectures that we've had in the last few chapters, where really I'm re-recording certain videos in order to support the transition from the old textbook to the new textbook. So in these middle modules, if anything I say kind of sounds inconsistent with our book from this semester, just note that it is the middle modules are again a recording from prior semesters. So first and foremost, let's introduce this idea of rigid body equilibrium. What does it mean? Well, maybe it's easier to understand what it means by comparing it to the type of equilibrium analysis that we already did 2 chapters back. So if you remember 2 chapters back, we introduced the idea of particle equilibrium analysis. And one of the ideas that we really hammered home is that doing particle analysis doesn't necessarily mean that the body is small. It just means the loading conditions are such that the lines of action of all the forces acting on a body pass through a single point. And in that scenario, we can model the body as a particle, not because that it's physically small, but because that type of loading scenario will result in a purely translational tendency of motion. And what that means is whenever a body is loaded like that, all that the forces could do if it weren't in equilibrium is move it, either slide it to the left, right, up or down, or front and back, depending on how many dimensions you're working with in that problem statement, 2 or 3. However, now we're dealing with scenarios where we have to consider the physical dimensions of the body, and we're calling that rigid body equilibrium analysis. And in rigid body equilibrium analysis, the actual dimensions of the body matter because the nature of the loading could produce either translation or it could produce rotation. So the only way that that body will be in equilibrium is if the sum of all forces acting upon a body, the resultant vector force, is equal to 0. And remember that depending upon the dimensional nature of this problem, this single vector equation to the left could yield either 2 or 3 individual scalar equations. But in addition to just having no tendency of translational motion, which is what the sum of the resultant force being equal to 0 means, in addition, we can sum the moments that the forces create about any arbitrary point on the body. We are free to choose that. And in any scenario, that will result to 0 as well. So physically, what this equation on the left means is it's not going to translate or shift in any dimension. And this equation on the right means that it's not going to rotate about any point, which generally speaking, since that point is arbitrary, just means that it's not going to rotate along any axis or in any dimension. So in order to be able to enforce these types of equations, clearly we're talking about equilibrium of a body. The kind of tool that we use in static analysis is something that we've seen so far, and it is referred to as a free body diagram. So it's always going to be the first step in any type of static analysis that we do. So when you think about performing or drawing a free body diagram, this is something that we've seen multiple times so far in the course. The first thing that we need to do is actually ask ourselves, what body are we analyzing? And typically that's going to be told to us through the actual problem description, particularly at this point. And usually the problem descriptions are intended to mimic real-world use cases that you'll encounter as an engineer, where you're asked to determine whether or not giving loading on a structure will produce forces that would exceed the rated values that support structures can actually support, for lack of a better term. So we have a roller and a pin type support structure here. We have a truss that's loaded with a specified mass. In the analysis type domain, we might be asking ourselves whether or not this loading will produce reaction forces at the support that exceed the rated values. So it's kind of an analysis, engineering analysis type problem. So in this case, the body that we're going to analyze is the truss for the free body diagram that we're drawing below. Now remember that we're in a free body diagram, we're replacing the effect of anything that we've removed from that body by the equivalent force that what is removed would exert on the actual body itself. So we're fundamentally, what that means is that we're drawing forces on whatever body we're drawing the free body diagram of. And forces are vectors, so they are described by both a magnitude and a direction. However, forces are unique in the sense that they're also differentiated by a point of application, which determines their tendency to exert rotation, as we've spoken of previously. So we want to make sure that when we're adding these forces into our free body diagram, that we're consistent to add as much information as we can about where the force is applied, its magnitude and direction, which we may know or we may not know. If we don't know it, we simply indicate it by an actual variable, as we've done for these reaction forces. We'll define the idea of reaction more formally in the next slide. But your book here in the 2 bullets just separates the set of forces that are actually the loads on the body, so anything that's applied or the actual weight of the body, versus the 3rd bullet point here being the reactions, which typically we won't know at least some parameter of. Usually the way that the book tries to actually model these is by always having the reactions only have unknown magnitude but known direction. So in the case of this pin connection, if you notice, if you have something physically pinned to the wall, it can oppose the tendency of the force of the body to translate in any direction. But rather than have an unknown direction, it's just easier to since 2-dimensional forces form a basis over any 2-dimensional vector, to just represent it by an unknown x component and an unknown y component, solve for those magnitudes individually, and then that kind of allows you to describe the arbitrary direction of this reaction force. Versus the nature of the support at B, if you notice this is called a rocker, all that it can do is push the body away from the wall. It can't support any translations up or down. So this pin connection at A is totally responsible for basically pulling this truss up when it's loaded by both its own weight along with the applied force. So really, bullet 1 is just about removing the body from its surroundings, and bullets 2 and 3 are about replacing anything that you removed by its effective force, remembering that we want to include external loads, weights, and any reaction forces, and we'll determine the nature of these reaction forces by using the table that were provided in our text, which we'll look at next. The final thing that we want to be careful in a free body diagram is that we include whatever dimensional information we need in order to enforce those equilibrium equations that we looked at on the previous slide. So one thing that you want to know, and we're going to look at this more in detail in the next module video, as I mentioned, so I won't go over it in much detail now, is that whenever we have a drawing in our text and we see the support structures and we want to replace the effect of those support structures when we're drawing a free body diagram by reactions, we want to classify them according to the nature of the support that they can provide. So if you look at the set of reactions or support structures that we're showing here, we have 3 different types, but all of these have a single unknown parameter to them. Namely, you only don't know the magnitude of the reaction force, you know the line of action. So in the case, if you imagine you have a roller support on a frictionless surface, obviously it can't provide any opposition to forces moving in the horizontal direction. It can roll freely. The only thing that it can do is push normal to the surface upon which it rests. So each of these 3 physical scenarios, even though technically they represent different things, and in the real world, since nothing is purely frictionless, they would have different opposition characteristics. For our case, we're modeling them all as a single unknown reaction force that is exerted perpendicular to the surface. A similar ideal here, if we have a actual body that's fastened to a wall supported by a cable or a short link member, we have already talked about the fact that the direction of that unknown reaction force has to be along the actual geometry of the cable or the link, but we don't know the actual magnitude of that force. If something is in a slot, or it's fastened via a frictionless rod and a collar, in that case, we know that basically all that this connection can do is pull it back towards the rod or towards the slot, and it's pulling in a direction that is perpendicular to the slot, kind of pulling it back in. So that's why the direction in this case is perpendicular to whatever the plane, kind of the axis of motion that the body would have. So a lot of these things are easy to see when you actually look at an example problem. Obviously, if there is friction and a body is resting on a rough surface, in addition to just being able to oppose downward motion and push up, it's going to actually be able to exert a bit of a horizontal reaction force in order to stop it from moving left to right. And for the case of a fixed support, if you imagine burying something like a post in the actual ground, in addition to being able to oppose motion in the downward direction and in the left and right direction, it's also going to be able to oppose rotation about the base as well, meaning you're going to be able to apply a torque and it's not just going to tip over as a rod would if it were just sitting on a rough surface. So in this case, this reaction is able to oppose both horizontal and vertical translation along with a moment at its base. So here's a little bit of an example problem, and I included this because it's kind of tricky, and I'm going to go through it pretty quick, but I just wanted an opportunity for you to think about why this is actually the right answer. So we're given a frame that we're told is intended to support some type of a portion of a roof structure. If you know anything about how roofs are constructed, the fact that you have this periodic maximum loading at some fixed distance is not really that surprising, just based upon the construction of roofs. But in addition, what we're asked to do, if we know the actual tension in this cable that's fastened at point B and is slipping over the pulley and ultimately fastened to the ground over here, which is going to help kind of stop the actual frame from rotating in the counterclockwise direction, can we draw a free body diagram of this actual part assembly, which I'm looking for the name that they're actually calling it here. Oftentimes these, I guess they're just referring to it as a frame. A frame, as we'll see later on in the course, generally in static analysis is just a connection of multiple members. So usually I wouldn't call something a frame that had this cable and pulley system connected as well, but that's okay. So how are we going to go about actually drawing the free body diagram? Well, here they're giving us 4 different free body diagrams, and they're asking us to choose what is the most appropriate. So hopefully you can look through these and ask yourself, it mentions discussing a neighbor, but in an online asynchronous course, obviously that's going to be hard, but take a minute and ask yourself which of these is most correct. Well, remember that fundamentally, a free body diagram, if we're attempting to, from an application point of view, usually what we would be trying to do here is to determine the unknown reaction forces or the stresses that are being put on the support by the loading in this particular scenario. So clearly item D is not going to be correct. Why? Well, if you look, the actual cable that is supporting this structure is shown as still physically connected to the ground. And remember, in drawing a free body diagram, the first thing you want to do is remove that actual body away from all of its support structures and just replace the effect of those support structures by an equivalent force. So since the actual frame and cable assembly isn't removed from the ground here, D is clearly going to be incorrect. In addition, if you kind of just look at a comparison between A, B, and C as you're first getting started, oftentimes it's hard to actually draw something from scratch. Maybe you can just look at the differences between them and ask yourself what is different about them and whether or not those different things makes this correct. If you look at the free body diagram that's drawn at point A, the only effect of removing the cable that you see is 150 kilonewton force applied at point B. And that is acceptable because the tension in this cable is 150 kilonewtons. But remember, if you remove physically the cable, you also have to account for the fact that it's passing over this pulley, and it will be exerting a force on the pulley that's pulling it back down to the left, along with, and we've done an example of a free body diagram of pulleys before, a force that is pulling it back towards the ground over here to the right. So hopefully everyone sees what I mean by that. Free body diagram A neglects the actual forces that the cable exerts on the pulley portion of the frame. So in C, you actually have those 2 individual forces included. However, even though this is correct, if you just leave the cable there and basically view the entire body as both the frame and the cable together and just show for that kind of aggregated body of the frame and the cable, this 150 kilonewton force pulling at the bottom of the cable, B and C are actually the same thing. However, B is going to be a simpler free body diagram, and that's all that this is saying in this case. So D is not correct because you haven't removed the body from the actual ground. A is not correct because you're not counting for the effect that the cable exerts on the actual frame around the pulley. B and C are equivalent. However, in B, you're not showing this cable actually separated, which isn't necessary in order to determine the reaction forces at the base here. You can just take these equal and opposite forces and not even show them, view the assembly as the frame and the cable, and work with this simplified free body diagram that you see in part B.